Okay, any questions? Okay, the big kind of centerpiece that we've had recently is the fundamental theorem of calculus. So, if you're confronted with this problem, and if you're in engineering or science, I promise you're going to be confronted with this problem a lot. You got to do some kind of interval to figure something out. And this is where f is in antiderivative of f of x on. And this actually works if we were at continuous function actually. So what this means is getting an answer to this is easy. If, big if, if you can find this, if you can find big F, then all you gotta do is plug in 2 points to subtract. Easy peasy on the squeeze, right? So here's the big F. You can find that. And so the kind of problems that we saw at this point, that was usually not too bad, right? So if I want to go yes. You say, hey, that's my favorite antiderivative with cosine x, and it is. So this problem is easy. It beats the heck out of little boxes, sure, right? But what if I did this? Actually, instead of 10. Well, this one might be doable as well. I need an antiderivative cosine 2/5 x, right? So, anybody give me down the road a little bit? Yeah, for sure. There's going to be a sign there, right? Sign of. Yeah, it's going to be it's x. Because the derivative of this is cosine 2/5 x, but I'm off a little bit, right? Because what's the derivative of this? It's cosine of 2/5 x times, get that extra 5/2. Right, so if I were to take the derivative of this, I would get cosine 2/5 x for sure, but then I get that extra 5/2, or I'm sorry, the extra 2/5 because of the chain there. Right? How can I fix that? What's it? No, because then where are you going to get the cosine?
Oh, right.
And then there's going to be a product here. But actually, this one has a simple solution. Right? Because the derivative of this is 5/2 cosine blob, and notice the 2/5 magically cancel. Right? So this is 5/2 sine of 2/5 5 minus 5/2 sine of 0. Well, this one was a little bit more hard to come up with. So, and by the way, what were we trying to fix here? We were trying to fix the chain rule, right? Because when we naively guess that, we got that extra 2/5 out, right? And we use that to fix it. So what we're doing is we're comparing the chain. There are two major rules, major techniques of finding antiderivatives. U-substitutions and integration by parts. I'm going to teach you both of them. You're going to see some other stuff in a trig substitution. That's a special case. And you're going to see partial fractions as well. And that's not really calculus, that's algebra. So let me give you the substitution. And this covers a lot. And the rules seem simple enough. But then I'm going to, there's lots of ways to implement. So let me give you sort of the mathematical background here. Let's suppose B and f of x continuous. Then f of g of x, g prime of x, dx is f of q. And notice this is actually antiderivative, right? Because the symbol is that antiderivative. You have a definite interval. You change variables. So now let me ask you this. Show of hands. How many of you have seen u-substitution before? You ever? Did you talk about it in 1040? Okay, right. Well, it may have been similar actually. Okay, so the idea here is what everybody agreed that this one here on the left is more complicated than the right. Like it's all chunked up. The idea here is you do the substitution, you do the g of x, and you make this thing in here simpler. G of x now becomes u. And this bit right here when you do your substitution, u equals g of x, do this just like we did when we did differentials. Right? Du is g prime of x dx. This is your du piece. Here you're integrating with respect to x. Here you're integrating with respect to u. The variables are slightly different. So in the old days, when x was a, new limit should be g of a. In the old days, when x was b, x is b, then u should be g. All right, so let's just do a zillion examples of this. Let's do this one. Okay, this is a simple one. We might do it later, but let's start on this. Let's say that I want to do everybody agreed with 2/5 inside here was giving me a bit of a headache, right? I can write down the antiderivative cosine x, antiderivative this, a little confusing. So, one thing to try is turn this confusing piece into an easy piece. U is 2/5 x. U, the derivative of 2/5 x is 2/5 dx. Now let me point out that this means that dx 5/2. So this becomes cosine u. And instead of dx now, I've got 5/2 du. And let's change our limits. In the old days, x is 0, and if x is 0, the substitution tells me u is also 0. And in the old days, on top, x is pi, and substitution tells me now it's this. So this is 5/2 interval 0 to 5 cosine u. Now I have an integral that I know the antiderivative is cosine. The antiderivative of cosine is sine. So I get 5/2 sine 2 to 5 minus 5/2 sine. Same thing I got up to. But now I've got a systematic way to do it instead of all this guesswork we had. Anybody have the antiderivative of 2x over square root of 5 off the top of it? Right? That's what I want to do. I want to write down an antiderivative of that so I can put it in. Oh, that's a good log of what? Good. Yeah, you're exactly right. Yeah, the antiderivative. Not bad. The log of x squared equals 5. You see it? So, but maybe I'm not quite as clever as you are. So let's try this. Any ideas on what a u-substitution is? And I will tell you that sometimes you can get really clever and pull some substitution out of the Stephen King novel. But most of the time, what you want to do is you want to try to piece this, right? U equals top, U equals bottom. U equals bottom is often a good attempt. If you have a square root, what's under the radical? Let U be what's under the radical. Sometimes it's good. If you have an exponential, U is what's up in the exponent. That's a good try. But try anything. Let's try U as bottom. So if I do this, U is going to be what? What's the derivative of x squared equals 5? 2x. And don't forget your dx. And look at that. That's so nice. Because this piece right here is being 2x dx. And this piece right here is being. This is going to work out. It's going to certainly simplify. This is U. That means log. Don't forget, change your limits. In the old days, x is 0. And if x is 0, what is u? So 5. Look at the top. In the old days, x is 3. So in the new days, you should do what? Yeah, that substitution equation you not only do you use pieces in here, but you use change limits. Now, this thing much less complicated looking than the other. So, what's your favorite antiderivative? 1 over u. Natural log of the absolute value. I don't really need absolute value in this because u's always positive. So I get natural log of 14 times natural log of 5, or like look in this laws. Questions? Okay. How about this? Just find the data. This is my never give up. Yeah. That's you might be able to do that work. What's giving you a headache? The 1/2 power, right? So he tried the substitution bottom is the whole square root, right? It's a good idea, right? But the problem is take the derivative of this and you get the 1/2 and the minus 1/2. I think you might be able to make this fly. But I'm going to need your idea. Let me give you some advice. Always try simple first if possible. So instead of doing this, I'm going to rip off your idea and do that. Because it's easier to make the break. Right? And if this doesn't work out for me, I can always unfold. Right? If we go with this, what's du going to be? It's going to be 2x dx. Right. Now let's put our eyeballs on this and see. I'm going to rewrite this here. Does anybody see an obstruction? I mean, this last one was so easy, right? Bottom was u, top was du. There we go. What's the problem here? Right, u is equal to the top over here, but here I don't even have a matching power. So, I mean, I could do this. Notice that I have so this might be clever rewrite. Everybody agrees it's the same thing. So it wasn't the same thing. Everybody agreed that this and this is the same, right? Because the 2 cancels the 1 out. Oh, why did I write it that way? Where is it? Why did I do that? Right. This bit right here is du. I'm kind of analyzing what these parts I've done, right? Oh, right here. Derivative d. So if you have u is this, then du is the derivative of this dx. Everybody agrees that I've got u here, I've got du here, right? But dang it, I've got 4 powers of x left over. That's a problem, right? Because you can't mix and match. When you do a substitution, you've got to totally get rid of your x and get an invariable in. You can't have some x's and some u's. You got to do a complete purge and rewrite. And now with this, it looks like a totally hose, right? Because I've got that extra. What am I? Everybody see what the problem is? This is a du, got that covered. This is a u, got that covered. I've got 4 powers of x. So you can only have one of those, right? So there's only one dx there, but I think you might be on the right track. Yeah, you were trying to do another substitution. You've got to make everything work off of this one substitution, and there can only be one du and dx, and that can't be in the bottom of the fraction. That's another thing. Let me rewrite this creative. Another way to write these substitutions. And what do I have to get rid of? Can I turn that exponent into all units? Yeah. So this exponent is actually u minus 3 quantity squared. Everybody okay with that? So if I implement the substitution, then this becomes integral of 1/2 u minus 3 quantity squared u over u of 1/2. And now it's completely turned into u's. Square root of both sides of this. Square root of that, x4, square root of that. Everybody okay with this? Why are we better off? Right? I mean, look, I went from this, this, but I really improved my situation. So let's go a little further here. It's 1/2 u squared minus 6u plus 9 over u to 1/2. Right, okay. We multiply that 1/2 through, and I get 1/2 u squared minus 3u plus 9/2 over u1/2. Now, use the algebra to help you out. Write that as 3 separate pieces. So we have 1/2 u3 minus minus 3u1/2 plus 9/2 minus 1. This is this, this is this. Right. That's kind of the cool thing with the single thing. The final answer to show you here are now wielding some power. Because this is, right, I'm not there, 1/2, this is u to the 5/2 over 5/2 minus 3 u to the 3/2 over 3/2 plus 9 over 2 u to the 1/2 over plus. So this becomes 1/5 u to the 5/2 minus 2 u to the 3/2 plus 9 u to the 1. And what do you suppose the final thing we need to do is? My original interval asked for antiderivative x. You got to so go back and use your substitution equation. This is 1/5. See what u x squared plus 3 5/2 minus 2 x squared plus 3 3/2 plus 9 x squared plus 3 1/2. This is some real power because what this problem shows us is the antiderivative of this is this. You're not going to guess it. Right? You can always check these, by the way. If you take the derivative of this and are patient with it and simplify it, you'll get this. Yeah. I wrote it this way. This fraction here. And I simplified all of those. Okay. I want to find a function whose antiderivative, or yeah, I want to find the antiderivative of 6x into x squared. Okay. Any ideas for substitution? If you're really clever, you can solve something with substitution. You can always do it with one solution, but don't, or that is with one substitution. But don't let that hold back here. Sometimes it's good to take baby steps. This I'm asking, can anybody see any kind of substitution that you can do that might make this problem with a little bit more time? Not quite as fast. Okay. If u is 3x squared, that's going to make this just tangent u, let's say. And what's my dx, or what's my du? 6x dx, and that's just what the doctor ordered. Because this is du, and this is u. So just becomes much simpler looking problem. I agree with that. Now we've actually done this one before, but it was a little bit flaky. I kind of showed you last work. How could I make this solve this problem? So now I've reduced my first more difficult looking problem into something simple. Instead of 6x tangent 3x squared, I've now just got to play in tangent. But I still don't know the answer to it. What you do in trigonometry if you're dealing with trig functions that, you know, are a little bit less familiar? What's true of all trig functions? They can all be written in terms of what? Sines and cosines. So let's try that. This is actually sine u you guys see a substitution that might help us out here? Let me call my new variable z. So can be the other one. What substitution could I do here that might help me out? Z equals what? Let me actually point out the side here. What is one substitution that will never work? If I have, I can do something crazy. What substitution here will never work? If you did the substitution u equal x, that will never work. That's why I explain why. All you're doing is changing every x into u, right? And so what you get is f of u du. No progress. That'll never work. Now, variance of this will. Sometimes the substitution u equal negative x will work. Sometimes the substitute u is 1 over x will work. The u equal x is just the source of part A. You'll just change all your letters into something else. It doesn't change anything. Whereas, notice this made a qualitative change. Oftentimes, when I see a fraction, I'll look, what's the relationship between the bottom and the top of this fraction? Relationship. The calculation. That's right. The top of this is almost the derivative of the bottom, right? It's off by a sign. That should be close enough to rock and roll. C is cosine u. And dz. Somebody remind me, derivative cosine is? negative sine u d. Now with this substitution, this becomes, I get a z on the bottom, and I almost get the top, I get negative 1. And after all this work, after my two-step process, I finally see something I recognize. The antiderivative of 1 over z is log z. So this should be minus natural log absolute value of z. Now, this is unsatisfying because my original variable is x or an antiderivative. So this should be minus natural log absolute value of cosine u. Let's see. So that's what z is. Still unsatisfying. Going back to the original x, u is 3x. Or if you like, this is natural log. There's one there's no way you could have done before. How about this one? I want to find the integral from e to e squared of 1 over x log x. Anybody know the integral of x log x? 1 over, actually it's not even that, it's 1 over x log x. The antiderivative of that off the top of your head? The problem is, what happens to take the derivative of that? Right? The 1 over x bit that you have, that's derivative should be 1 over x squared, and that's nowhere in. Right? Okay. Try use substitution, see if you can make this easier. You know, the first line of what you're trying should be a piece of this. Piece of the C you're trying to integrate. Anybody want to try? So, U equal what? That's a great idea. Let's do log x. So it might be tempting to write 1 over log x. It's too hard to take the derivative of that. Try the easy first. And I can tell you already, this is going to work. Anybody tell me what the U is? 1 over x times dx. So this bit right here is your du, and there's your u. How about that? And you can see actually there's an art to this, right? You have to try things. It's not, there's not any kind of rule that says if you have this function, you do this. You have to try things. Okay, so this becomes, let's see, this is 1 over u du. Everybody see that? The dx over x is u and 1 over u. Are you okay with that? There's no cancellation. See, this dx over x, dx over x is the same thing as u. That's what this bit says. And here you have dx over x. That's the same thing. So I substituted this in my du part. Du is always going to go in there. And what's left over is 1 over u. Well, what else do I have to do before I'm done with this step? I need to change my, that's right, I need to change my limits. In the old days, let's look at the bottom. U is, I'm sorry, in the old days, x is e. And what's the log of e? Bottom one. In the old days, x was e squared. What's the log of e squared? 2. And now what do we have? This is natural log of u. So we get natural log of 2 minus natural log of 1, which is natural log. So that interval is the natural log of 2. All right, let's have a little fun with trigonometry here. How many of you remember your trig identities? Maybe you know that there, maybe you don't know it. Anybody know what sine 2x is? Actually, that's sine 2x right there. But those are not quite as fluid, right? Calculus will always help you remember your trig identities. I'm going to do this problem 3 ways. Okay, think of a u-substitution. U is what? This is your big chance to get because you almost get it. Why? And so if u is cosine, what is du? Negative sine as dx. So this becomes 2. This is u, and sine x dx is going to be minus u. So this becomes, what's the antiderivative of minus 2u? Negative u squared. And u was what? Cosine? So I get minus cosine squared of x. Everybody agree with that? And by the way, you can check it. Derivative of this is -2 cosine x times negative sine x. So it's let's try using sine x. So now u is cosine x. Yeah. We don't have this minus signs from certain senses. Yes. Always make so this is 2 sine x cosine x. U is sine, u is cosine. So this is 2, that's u, and that's d. All right. So that's u squared plus c. And u was sine x. That's put it up here. Oh, because like first because the derivative of sine is cosine. The derivative of cosine is negative. Yes. What's the derivative? Now, does this bother you? So here's one for you. Derivative of this, check, is this. Derivative of this is 2 sine x. Also wrong. Now let me point out these two constants do not have to be the same. In fact, let's call that C1 and C2. But what we get is so let me kind of make a little observation here. Sine squared x and negative cosine squared x are both antiderivatives. 2 sine x cosine. On any interval. If you have two functions that have the same derivative, what's true about it? They vary by sign. So this means sine squared x equals negative cosine squared x plus some constant k. And I bet you it's going to be that constant always is. It is 1. Because which in this case must be, right, that's all that all three I think. Here's another one. If you're clever, you might have noticed that. Right? Those 2 sine x, cosine x is the same thing as sine 2x. Here, let's do this. So dx is 1/2. By the way, I'm used to writing my u substitutions. U equals something function of x. If you can ever write your u substitution x as a function of u, it often makes it easy. I'll show you exactly that in a moment. This is equal to the antiderivative of sine of u. My dx is 1/2 du. What's the antiderivative of sine? Negative. And u was 2x, right? Also note that and minus cosine squared x both are antiderivatives. Sine 2x on the interval well, everything. And so they must vary by constant. Well, so what this means is minus 1/2 cosine 2x is equal to minus cosine squared x plus constant. Let me multiply this by minus 1/2 and cosine 2x is equal to 2 cosine squared x plus some other constant. Anybody know what that constant is? All right. These two are both antiderivatives of sine 2x, so they must vary by a constant, but the mean value for them. So you cosine 2x, it's supposed to be true. Cosine 2x, cosine squared x. How can I figure out what that constant is? Everybody agree it does vary by a constant? Question, what is it? What's it? It's quite too. There's a way you can figure it out. Since it's a constant, you can plug in anything and figure out what it is. What's the easiest thing that I can plug in here? Well, I'm going to. That's going to be cosine 0, 1. It's 2 cosine 2. Okay. And I get K1 to negative 1. So I get this identity. That's no trig identity. You can also get the identity for 1 minus 2 sine squared x cosine squared x minus. So this calculus recaptures a lot of trig identities. A and B. Notice that previous problem, I did it 3 different ways, all with u-substitutions. I'll do it slightly. Okay. Any questions? I'm going to show you another trick. I'm going to do a couple of things. It's fun, I think. By the way, you know what the answer is. Yes, but remember, it's very tempting when you see like fractions, constant log. This isn't a log. It's C inverse 2. That's right. C inverse 2. Now, we just did this, right? And we said, oh, look, you remember 1040 that the derivative of inverse tan 4 of 1 was x squared. It's the antiderivative. I'm going to give it to you in the direction. I'm going to need to remember a couple of things. You'll have to keep up here. And so I get tangent squared. I divide this equation both sides by cosine squared. Now here's a substitution that you might not have guessed until maybe this right here. But what if I let x equal tangent theta? Right? I mean, what orifice did I pull that out of? Well, there's a logic. So let's see what happens. But forget about the u, forget about the substitution for the moment. What happens to that bottom if I plug in x tangent theta? I get 1 plus tangent squared theta, right? Which was awful until I look at this. Tangent squared theta plus 1, just 2 terms. Now a single. Maybe I can do something. Okay, so let's just go with this. If I do this, what's dx? Anybody remember what the derivative of tangent is? Secant squared. There you go. So let's see what we got. This is dx is secant squared theta. And this is 1 plus tangent squared. Right. And this is secant squared theta over secant squared theta. Right? Using the same. Everybody okay with that? This is super fantastic. What's the antiderivative? 1. Not x in this case, but my variable. And what is theta? Making my substitution equation and realize that theta is the inverse tangent of x. So I get. So now we come back to the antiderivative of 1 over 1 plus x squared. Here's another one of this ilk. I'll do a couple more. This was like example. I'm going to do this one. What is it? Let's go to the antiderivative. This is a special kind of substitution called a trig substitution. So was that one, and you'll study this quite a bit in Canadian. But I do this example in the next one to show you that sometimes there are clever things to do when you think about the problem. Most u-substitutions are a little bit more routine, like what we've done before, but these are a little bit clever. I don't know what you do not know off the top of my head, the square root of it's not. The square root of x squared is easy. So you just take the square root of it. What's killing me here is I'm running this. I want to take advantage of this. Right? That is. Unfortunately, this isn't a 1, it's an R. So let's do this. Here, I'm going to assume R is some number. I'm going to show you. I'm going to show you what it was. Let me ask you this. Let me take a little aside here. Forget about the. Well, no, we'll go ahead. If I do this substitution, what is the x? Remember, R is a constant. Derivative of sine is. Now, why is this going to work? What's the motivation behind this? When I put in r sine theta x, that's right. That's right. This is essentially, see, this takes advantage of, I don't have any limits on this. It's finding an anti. When I plug in for x, I get r squared sine squared theta, right? Which may seem worse, but now, because of that r, I can pull that r out. Agree? So this is r right. Now, what's 1 minus sine squared theta? That's exactly right. And instead of 2 terms, which really ruins my day, I'm now going to simplify. And the square root of cosine squared theta, well, it's actually the absolute value of cosine theta, and somehow we got to be a little careful right now. So now, in terms of square root, something more complicated. This is r cosine theta. And what's the x? Also, r cosine theta with a d theta kicked on. So this becomes r squared cosine squared theta theta. Now, okay, I've turned a square root into a square root trig function. How am I going to interpret cosine squared theta? Now, I think right here, eventually need another trig out of it. Sometimes sine squared is thing. might not remember this, but you see it's the same point. So here's why this works. This is r squared. This is 1/2 of 1/2. Now, I can write down the antiderivative 1/2 theta. And this one is really another u substitution, but I'm just going to go ahead and forego that. If I take the derivative of this, 1/2, and then since chain rule, it's going to be cosine 2 theta until 4, so it's going to be. I'm all right, I'm understand. In this last step, what I did is I used the identity we talked about earlier, sine of 2 theta, sine theta. So replace the sine of 2 theta with 2 sine cosine. There's your answer. Now, this answer is terribly unsatisfying because didn't I ask for the antiderivative of this in terms of x? And now I've got this crap in terms of theta, right? Not very satisfying. How do I do that? How do I turn these thetas back into x's? Right? See what I did? I did a magic change, and then I said, "Oh, I can do this," and I did it. And there we go. There's an answer. But now everything's in terms of theta instead of x. Any ideas? So here's what I've got. I've got r squared 1/2 theta plus 1/2 sine theta cosine theta. Any questions on how I got up to this? These right here, previous courses, these are just trig identities. And if you ever needed those, you probably did. Why didn't you? That is a great question because it's not clear until maybe I did this. Remember how this substitution, because 1 minus sine squared is cosine governed in square root for us? That was really the whole motivation behind it. But where did I get this? I know how to do it, right? I mean, it's just experience. I learned this stuff too. This is a trick somebody came up with that works for this thing. You're going to study this in depth today. When we get to a second trig substitution, we're going to show you the field of this. But the point of this example is sometimes substitutions that are maybe not obvious workflow. Well, does everybody understand the steps? Yes. How do you get rid of the what? The 1/4? Oh, because this is, that's exactly right. This bit right here is 2 sine theta, and the 2 cancel. Okay, other questions. The last thing is I asked for the antiderivative square root of r squared minus x squared, and I get the scrap with theta. That's just not cutting. So go back to your substitution equation. So one thing you can get is theta is inverse sine of x over r. Everybody agree with that? So you can just shove that into theta everywhere you see willy-nilly. It still might be a little bit unsatisfying, better than this. So this is a little bit of trig. Draw a right triangle. I have an angle here whose sine is x over r. What is sine? There's the sine theta, right? What's the missing side? It's like Pythagoras. Square root r squared minus x squared, right? That's something really. Now, this is r squared 1/2 theta. Well, theta is the inverse sine of x over r. I can do better than that. However, read the triangle. Sine of theta, x over r. Cosine of theta, this over r. There you go. So I can multiply this through r squared, and r squared over 2, inverse sine, x over r, plus r squared is cancel that, 1/2 x. There's the antiderivative. If you take the derivative of this, you will get square root of r squared minus x squared. And this shows you the power of substitutions, because you're not going to guess this looking at that, are you? Right? You're not going to guess it. And this is why antiderivatives are more difficult, right? Substitution is not obvious. And again, don't confuse the inverse sine with 1 over sine. Right? That's the inverse. So you're good with this one, right? There's 2 r's here. And it cancels the r squared.
Oh.
Okay. I'm going to do one more of this stuff. These are like hard substitutions. If I ask you something on the quiz or test, which I will give you some guidance on this. I don't expect you to pull x equal r sine theta out of your math at this point. What if we did this? Find the antiderivative. Let's go. Squared 5. We should get it. I'm gonna remember how we just did inverse tangent. I'm gonna do the same type that I did here. Only here I've got it wrong. Again, let me justify this. What is the whole idea behind this? The whole idea behind this is a sum of 2 things, which is awful. I'd like to get it as a single. I'm trying to take advantage of this. Tangent squared plus 1 and secant. Here's why this might work. If you have 5 angles, then if x is r tangent theta, then this becomes r squared tangent squared theta plus r squared. Multiply that. I can pull an r squared out of this. And this is so what happens when I take 5 half power of this? Or what power? Yeah. And secant. Now, if x is this, then dx is going to be r derivative tangent squared so this is, if I just step back in, r secant squared theta and theta. And I've already worked this out. Isn't this like r to the 5th secant 5 theta? Everybody with me? This was awful, but what's another way that I can like secant squared divided by secant 5th? One over secant cubed, and what's 1 over secant cubed? What's 1 over secant? Cosine. So this is 1 over r whole, 1 over secant cubed theta. Right. And this is 1 over r4 cosine cubed theta. Doesn't work. You chain rule, you have a sign. I need to do u-substitutions. Why not? Let's do this. Thank you again for the substitution. Actually, this depends on the trig I think. Is there another way that I can write cosine squared theta? I did it. Okay, so this is what this does for our situation. Right, we'll get to that. Any idea what the substitution? First instance, we would go simple. Right? Don't do the whole 1 minus. Let's just try this. Here's my logic. If that is u, what's my e? There's that's stuff right there. This bit is going to be du, right? And I've got that clump taken care of. And what's this going to be? 1 minus u squared. And that, friends, this becomes one over R4, 1 minus u squared du. So this becomes, what's your favorite antiderivative? Remember my variable u, what's the antiderivative? This piece is just u, and this. Okay, now we need to put back. Okay. What was u? It was sine theta. It's sine theta. Minus 1/3 sine cube theta. Let's see. And I can wiggle it in here. Now I need to go back to x. So how am I going to get back to x? Use the first substitution. Well, this one right here, we have x over r is tangent theta. We'll draw a triangle. You're finding theta. X over r, that's what? Opposite over adjacent. And so the missing piece is x squared, square root of x squared plus r squared. I see it right. Well, so the sine theta, somebody read this triangle, tell me what's sine theta. It's x over the square root of x squared plus y. Correct? So, barring any mistakes that I made along the way, so I think I did. This is x over the square root of x squared plus r squared minus 1/3 x cubed over x squared plus r squared 3 times. Take the derivative of this. That. Any questions? So you feel like you're kind of getting how this works? Right. Is again, what you're doing is you're just trying to undo a substitution. Questions? All right, y'all feel like you're ready for the quiz? I don't know. I'm going to give it to you take home. So I'm gonna put it up on the somewhere. It'll be on my website. Put it on ends. You don't have a time limit. There's 40 points for the top, so there's like 8 problems, but 35. I can't do 35. Anyway, work through it, bring it to me first class tomorrow. Okay. So I want you guys to practice this and don't limit yourself to quiz, right? Work on other stuff. Okay, so these last three examples I did are really u-substitutions. When you get to 1080, this is going to be a whole section. They're going to call it trig substitutions, but it's just u-substitutions. Hey, you have to be clever, and they show you, oh, if you see this kind of form, use this. You know how it's in the x squared plus r squared and r squared minus. They'll say, oh, do this, but it's all just a special case of substitution. But even without that, there's nothing. I love this one. I don't know about y'all, but I've always wondered, what is the antiderivative of 1 over the sum square root of x plus 2? What we got to do is, well, what's the first cosmetic thing? Maybe not going to change anything, but it just might put my eyeball on it. Yes, right. I mean, what am I, Gandalf here? Nobody likes to write this in this kind of form here, so let's do this a way that's more easy to digest, perhaps. That's what I'm really doing. Now, okay, good for me, but now what? There's a lot of things to second this, right? One of the things is in the denominator, right? If this were just x to the 1/2 plus x to the 1/3, I just integrate it, right? You just write it down. But the denominator, it's killing me. And number two, what's another thing you always think about this? Fractional power, right? Nobody wants that. You might think of a substitution where I can at least get rid of the fractional powers. That might be good, but if u is the denominator, I think that the u is because there was some. I want to sort of see it. Now, like I said, 90+% of u-substitutes you're going to use your 12 steps in here. And this sort of does, but it also it's not in the following substitution. U equal x of 1/6 now. What? Why 1/6? Can somebody tell me what I am thinking here on the right on the precipice of insanity? Why 1/6? That's exactly right. 6 is sort of a multiple of 2 and 3. In fact, it's the smallest multiple, right? So really, if this were the case, then what would x to the 1/2 be? Right, x to the 3/6, so it would be u cubed, right? And what would x to the 1/3 be? U squared. So at least that's what's going on in my coconut is that I think, well, maybe I can turn this into, that's going to be a cube and that's going to be a square. Maybe it's a little better. All right. Okay with that? Instead of right now. That's logic. But also be the du. What's the derivative of what's du? It's awful. 1/6 x to the -5/6 again, right? Don't do the substitution. Right? Right in this one. It's the same thing, right? But now you don't have to, again, you don't have to deal with fractions. if u is x1/6, then u6 is x. In fact, I will tell you this, and I mentioned this before a little bit. If you can write your substitution instead of u as a function of x, if you can write an x as a function of u, it's often easier to implement. In fact, these trig substitutions that I did right here, this was x is our tangent theta. So actually, x was the dependent variable if theta was independent. This made replacing the dx easy, right? Because dx is just what that derivative is. So 6u to the 5 du is dx. Everybody okay with it? Now, let's put this all in and see what happens. Dx is 6u to the 5 du, and this is u cubed, and this is u squared. And you know what? This one's a whole lot better than this. And there's something even better one. See what happens here. There's an improvement. You can cancel 2 powers of u in the top and bottom. If I agree with that. So this is actually 6u cubed over u plus 1. I think we got one. And now I see a substitution. Anybody see a substitution? Anybody see a substitution? You can perhaps give a try to. The only bad thing left is denominator is some. If it were just you, I'd divide out and integrate it, right? Once a substitution turns this into a single thing. Remember, simplicity is almost always the first step. So let's see the bottom. And so dz is equal to what? 1 du. So this is going to become, that part is c, this part is dz, right? What about the distance check? Good, that's right. You all learned from that. Go back to the well. Use your substitution equation. This is 6z minus 1. So, where are we at now? Interval 6. I'm going to cube out that business. Z cubed minus 3z squared, 3z minus 1 over z. So now, It's just a matter of writing it out separately. 6z squared minus 18z plus 18 minus 6 over z. Now, this should be fairly easy. Antiderivative of 6z squared. Antiderivative of 18z. Antiderivative of 18. Ooh, I can do that one. Antiderivative of 6 over b. What's constant? So now we've got to remember this equivalent in terms of this. So back to see. Everywhere I see the z, I'm going to put a u plus 1 now. And finally, my u is x. This is 2 x 6 plus 1 2 minus 9 x 6 plus 1 squared plus 18 x 6 plus 1 minus 6 natural log outside x 6 plus 1. I bet you would never guess the antiderivative of square root of x plus cube root of x is this. What it is? Any questions on that? Okay. I want you all to work on this. Some of those may or may not be helpful. Quiz. Take about 5 minutes thereabouts to work on that. See if you can get an answer. When you get an answer, raise your hand. So you want to know, right? That's right. That's one of the things about this. Substitutions. You know, important problems in your book and stuff. I think the answers in the back. And by the way, there's many different ways to write this. You look at this one right here. Notice a slight discrepancy. My answer here. It's the same thing. It's like, why is this thing here? Match, 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 match. But this is quite a match here. Why is it the same? What's different? Well, why is it? There's an extra, this has an extra 18 in it, right? This is just 18x to 1/6. This is 18x to 1/6 plus 18. The 18 can be added to the constant. Remember that problem I did where we integrated 2 sin x, cosine x, we did it 3 different ways? All of them look different. So many times the students come to me with, you know, the trembling lip and the tears in the eyes. Because, oh my God, I might be right back. Look, you might be getting it right. And you just can't tell. Because apparently we put our teams of mathematicians, it's perfectly natural looking answer, and you play with it till it looks like no human being would figure it out. But here's the good news. You never have to worry about the back of it. Take your answer, take the derivative of it. If you get back where you start, I promise you, you're right. Okay. Show of hands, who's got this? How far did you get? Oh, I didn't get it. So, what's the use of it? Or what should we do first to measure the size? See, one of the things that's right, sine 2x, cosine x, the angle is going to match. If I do this, they will. This, me, what's a good substitution? You always, when you do substitution, you be mindful of this. When you pick u, there's going to be a d. Ask yourself, can I take care of it? What's my du? And so I can take care of this. That's negative du. Agreed? And everything else is a cosine, which means that this substitution should work. Let's put it in there and see what happens. This is 2u negative d. That's my 2 cosine, and my sin x dx is over squared. Now it looks to me like I need another substitution to bail me out of this one. What's a good substitution? Agreed. By the way, sometimes, you know, I did say simplicity, and you might think that might be easier, but there's no harm in me doing this because when I take the derivative of 1, it goes away, right? So I'm not doing any harm. So this is going to be negative So it's going to be minus natural log absolute value of Z, which is minus natural log absolute value of vertical point. And this is minus natural log cosine squared. I can know what the absolute value is. I can also take them off there. How can I take off the absolute value? No, I said, notice how what my absolute value is. How can I get away with that? That's essentially it, right? Notice this thing right here, I don't care what u is, this is always positive, right? So the absolute value sign is what? Right? Because what you've got inside there is always positive anyway. Okay. Question. Sometimes u-substitutions just get you to another place where you know an answer without. So sometimes changing the limits. Well, here's a nice. Here's the surface power squared. Right there, you know. How many of you have ever seen ellipses? Like maybe not. Grab these things down. Well, see, like, remember what the equation, a circle is. That's a circle radius, right? Another way I can write this is x over r squared does this help remind you what the equation for ellipse is? It's similar to a circle, only it doesn't have constant radius. Is that look familiar? Well, notice it's just like a square, or like a circle. Because notice the denominators here are the same. The denominators here, both squares, they're different. And let's think about what happens here. If you trust a little bit, this should be it. When y is 0, what is x? Y is 0, the next is plus or minus x, right? And if x is 0, what's y? I'm drawing the b less than a, but it doesn't matter. What's the area of that? Well, let's do the top now. right. So y squared, b squared, 1 minus x squared, a squared. So y, the top half, b times the square root, 1 minus x squared. Right. This is the equation of the upper half of the ellipse. Right? It's not as nice as the circle, because guess what? B and A not necessarily the same. So take area under curve and double the whole ellipse. Everybody okay with that? So this is like one of our old school kind of calculus problems here. There's my doubling it, and it should be from sketch of this. Remember? It should be the integral of b square root 1 minus x squared a squared x. And what should my limits be? What's that? Better. There you go. Now this is another one of those trig substitutions, right? Which that makes real sad. But we don't have to do it. I'm not going to solve it. I'm just going to get it to the point where I recognize it. By the way, with all these examples, I'm not trying to teach you procedure. What you need to do is be creative, be logical, try to use stuff in there. But this kind of math will art is really your imagination. If I hate the sexual grade, I'm becoming. So let's do that. Let's do that substitution. Remember that what's the derivative of this thing? Correct. What's the derivative of 2x? 2, right? What's the derivative of 3x? 3, derivative of 4x, 4. What's the derivative of 1 over 8 times x? So, let's see what this does. This is still 2. That's a b. That's the square root of 1 minus u squared. The x is this is a. But agree with that. What else do I have to do? Got to change my numbers, don't I? So let's see how that's going to work for me. In the old days, x is a. If x is a, what is u? 1. How about the bottom one? In the old days, x is negative a, so u is negative 1. Now let me clean this up a little bit. Now I've got that much cleaner. I'm done. See if I recognize this bit right here. Brackets. What does that look like? This is the u-axis. What does this look like? This is a circle. This is the actual circle. Of radius 1. Correct? What is the area of the semicircle of radius 1? So this is 2AB. 1 half pi. So the area of this ellipse is 100% of d. The area of this ellipse notice that we did this problem using only our knowledge of the circle and the u-substitution. U-substitution turned this thing readily, recognize. By the way, this is also a good thing to do in computer science. Somebody explain to me why this formula that I got is this ellipse that looks like this. Why does this make sense? Okay. Right. So how do I make an ellipse be exactly a circle? What's the relationship between A and B here? They have to be the same. If A and B are the same, it's a circle. What happens if A and B are the same here? You get the formula. That's a good gut check. Hey, it's probably, it's not exactly right at ballpark. Okay, any questions? All right, so let me give you instructions for your quiz. I posted on my site and I posted on Canvas. It's just there's a file, download and look at it. You have unlimited time. Just do it yourself. I don't care if you use notes or whatever, but don't do a bunch of hocus pocus. I know you got it off some website. I need to understand your steps. So clear that up. Okay, other questions? All right, y'all have a good one, and we will see you tomorrow. Oh, yeah. Don't forget the evaluations and all that, and the meet with me. Also, we're going to do integration by parts tomorrow, and then we've got 2 blank days. There will be quizzes both of those days, and then we'll be working, but be thinking about, hey, Jim, I struggle with this hill. We're going to try to get everything sort of cleaned up. And by the way, also, another thing, since this is taken on with a lot of these antiderivatives, I'm going to actually is check yourself, right? Since you've got the time. When you get the antiderivative, you don't have to do it on the quiz, but just check it yourself. Take the derivative, see if you get it right. I am, in fact, right now. Okay, sounds great. What?